Hi everyone, this is Maverick Paul, the chemistry guru. Now in this video, we want to go through the second portion involving the suggested solution for 2023 A-Levels H2 Chemistry Paper 1. So let's take a look at question 11. The rate of an enzyme catalyzed reaction changes as substrate concentration changes. So which row correctly describes how the rate changes and gives the correct reason why it changes in this way. So the first column is involving how the rate changes as the substrate concentration increases, and we have two permutation involving the rate increases initially and subsequently decreases, or the rate increases, eventually reaching a maximum value. Then the second column, why the rate changes in this way. There are two explanations again. First one is activation energy is lowered but cannot go below a particular minimum value. Second explanation is all enzyme active sites are occupied at high substrate concentrations. So the topic tested in this question is under kinetics. Fairly simple exercise because for an enzyme catalyzed reaction, we actually learn explicitly that at the beginning, when the concentration of your reactant or the substrate is low, then it is going to be a first order reaction because you have enough enzymes to handle the increase in concentration of your substrate. So when you increase in the concentration of the reactant or my substrate, then I have enough enzymes to handle this increase in the catalysis. So therefore the rate of the reaction is going to increase. So this is the first portion before saturation, where the concentration of the reactant is smaller than the concentration of the catalyst, or the concentration for the substrate is lower than the concentration for my enzyme. It's going to be a first order reaction, and the rate will be equals to K concentration of my reactant or my substrate. But eventually, we're going to max out all my enzymes, and all the catalyst is going to be fully utilized, which is mentioned here. All the enzyme active sites are occupied at higher concentration. After that, when you reach saturation, then when you further increase the concentration of my reactant, there will not be any corresponding increase in the rate of the reaction because all the active sites are fully utilized and my enzymes are all working at maximum capacity. So increasing the concentration of my reactant is not going to increase the rate of the reaction anymore. Then the rate of the reaction is going to reach a maximum point. It doesn't increase any further. The second portion after saturation, it is going to be a zero order reaction with respect to my reactant. We want to view this enzyme catalyzed reaction as a combination of two graphs. First portion is first order with respect to reactant. Second portion will be zero order with respect to my reactant. Now we can answer this question. How the rate changes as the substrate concentration increases should be the rate increases, eventually reach a maximum value. And why this happens is because all the active sites are occupied when the concentration of my substrate is high. So answer to this question will be D. Next, how about question 12? The statements refer to the value of equilibrium constant Kp for a gas phase reaction. So which statement is correct? A, adding catalyst will increase the value for Kp for a reaction at equilibrium. B, changing pressure will decrease the value for Kp for some but not all gas phase reactions. C, doubling the pressure will double the value for Kp for first order reaction. D, increasing temperature will decrease the value for Kp for an exothermic reaction. It's a very simple question. The topic tested in this exercise will be on chemical equilibria. Now, we just need to keep in mind that equilibrium constant is called a constant for a reason. Equilibrium constant is only affected by changes in temperature. So if everything, all the terms can change K, then we can't call it a constant term anymore. So only changes in temperature will affect K. Straight away, we can rule out A, which is adding catalyst, B, which is changing pressure, C, which is also changing pressure. A, B, C, they're all wrong. D has to be the answer. Increasing the temperature will decrease the value for Kp for an exothermic reaction. Now, changing temperature can affect the K value in different ways, depending on whether the reaction is exo or endo. Let us try to quantify this and try to show that increased temperature will decrease the value for Kp if the reaction is exothermic. So I have a very simple process here, reactant to give me product. And if the reaction is exo, delta H is a negative value. And when there's an increase in temperature, what would the system do according to Le Chatelet's principle? According to Le Chatelet's principle, when you impose a change to the system and you feel that you're disturbing it, the system will actually try to respond, to try to counter or reduce or oppose the change that you're imposing. Increase my temperature, I don't like it, according to the system. So what I'll try to do is I will try to lower the temperature by absorbing excess heat from the surrounding, and I try to favor the endothermic reaction. So I'll favor the endo reaction to absorb the excess heat in order for me to counter this increase in temperature. Forward reaction is exo, reverse reaction is endo. That's why the position of equilibrium will shift towards the left hand side to favor the endothermic reaction. If POE shifts left, I'm going to form more reactant, so the partial pressure for the reactant goes up. I'll form less product, so the partial pressure for the product comes down. And if I sub this into my Kp expression, which is just a ratio of partial pressure of product divided by partial pressure of reactant, I'll have a smaller numerator, bigger denominator. My Kp will decrease. So answer to this question will be D. Next, how about question 13? The gaseous reaction between nitrogen and hydrogen is carried out. At equilibrium, temperature is 400 K, total pressure is 100 atmosphere. Initial N2 and H2 mole ratio is 1:3. Partial pressure of ammonia at equilibrium given is 92 atmosphere. And question is asking for the value for equilibrium constant Kp under this condition. Now, whenever we do questions involving chemical equilibria, and they give us information involving initial number of mole or pressure for my reactants and the partial pressure or the number of mole of species at equilibrium, usually what we will do is we will fill up the ice table, I for initial, C for change, E for equilibrium. Once I fill this up, then I can sub the partial pressure at equilibrium into the Kp expression, and then subsequently I try to solve for my Kp. So let us try to do this together here. Now, question tells me that the initial mole ratio for N2 to H2 is 1:3. We actually don't know what is the number of mole. So what we will have to do is I'll have to write this as X is to 3X. If the mole ratio involving N2 to H2 is 1:3, then the partial pressure for N2 to H2 will also be, according to this ratio, X is to 3X, because the partial pressure is proportional to the number of moles of that gas inside the container. So mole ratio 1:3, partial pressure will also be 1:3, X is to 3X. At the beginning, there's no product, so ammonia amount is going to be 0. And at equilibrium, the question did give me the partial pressure for ammonia to be at 92. So partial pressure for ammonia is 92 at equilibrium. So we have enough information to fill up this ice table. What I can do is I can try to fill up one of the change value for ammonia. Initial 0, equilibrium 92. So obviously this change in the partial pressure for ammonia is going to be a plus 92. Once I have this change value for ammonia, I will be able to fill up this entire row because it's comparing mole ratio. So the mole ratio involving the equation is 1:3:2. So this change row will also follow the mole ratio of 1:3:2. Another way is I can compare mole ratio involving N2 to ammonia is 1:2. So if ammonia, the change in partial pressure is 92, then this one will be 92 divided by 2, this would be 46. Because it is used up, it is a reactant, it's a minus sign. Then I can compare mole ratio between N2 and hydrogen, 1:3. So change in partial pressure for N2 is 46. Change in partial pressure for H2 will be 3 times of it. So this is 3 times 46. This will be a minus 138. So change row will follow the mole ratio of the balance equation, 1:3:2, 46 to 138 is to 92. Then I can add the two rows together. So this is going to be x minus 46. Add the two rows together. This is going to be 3x minus 138. Partial pressure for ammonia is 92. So basically what we have is, we have the partial pressure for each of these components in terms of x. But the question did give us this information, the total pressure at equilibrium is 100. So I can use that to solve for x. So we have this here. The total pressure is just the partial pressure for all my gases. Partial pressure for N2, and the partial pressure for H2, and the partial pressure for ammonia. And the total pressure is 100. Partial pressure for N2 is x minus 46. Partial pressure for H2 is 3x minus 138. Partial pressure for ammonia is 92. Everything add up is equals to 100. And therefore, I can solve for x. X will be equals to 48. And therefore, we will be able to solve for the partial pressure for N2, H2, and ammonia at equilibrium. So your partial pressure for N2 at equilibrium is 2 atmosphere. H2 is 6 atmosphere. Ammonia is 92 atmosphere. So once we have all these partial pressure, I can solve for my Kp expression, and my Kp will just be the partial pressure for my product raised to the power of the coefficient divided by the partial pressure for my reactant raised to the power of my coefficient. So it will be partial pressure for ammonia square over partial pressure for nitrogen and the partial pressure for hydrogen power 3. 92 square over 2 times 6 to the power of 3. I will be able to get this value 19.6, and therefore the answer to this question will be option C. Alright, next, how about question 14? Question 14, 30.0 cm cube of 0.500 mole per dm cube Br2 equals reacts completely with KOH to form 2.98 gram of KBr. The other products in this reaction will be KBrOx and water. So question is asking for the value for X in the formula for KBrOx. Now, in order for me to determine the value for X, I actually need the oxidation state of bromine in the product. Then I can figure out what is the value for X. So the topic tested in this question is actually redox reaction, and is a variation involving this standard type of question, which is to determine oxidation state involving unknown species given experimental data. But we have to do a bit of figuring out first. So first thing is, we know that based on the question given, I have bromine, Br2, reacting to form Br minus. K plus is stable, we can ignore that. To form Br minus and your BrOx minus. From the number of moles of bromine in the reactant, I can figure out what is the number of mole of the bromine in both products, Br minus and BrOx minus. Because by conservation of mass, the total mass of the bromine in the reactant has to be equal to the total mass of bromine in the product. When we apply conservation of mass, we will apply this based on the number of moles of your bromine in the reactant must be equal to the number of mole of bromine in the product. So the reactant I have Br2 converted to Br minus and converted to BrOx minus, the number of mole of bromine in the reactant has to be equal to the number of mole of bromine in Br minus plus the number of mole of bromine in BrOx minus. So that's the basis for us to determine the number of mole of BrOx minus. We need that first. I can figure out number of mole of Br2, no problem, because the volume and concentration is given. We can find that mole of Br2 is 0.015. Number of mole of bromine atom will be 0.03, twice of it. Then if I look at my product, Br minus, I have the mass 2.98 gram of KBr. I can divide this by the molar mass involving KBr. I can find the number of mole of KBr, 0.025, which is equal to the number of mole of Br minus. And the number of mole of Br in BrOx minus is going to be the difference between the mole of bromine in the reactant and the mole of bromine in KBr. Because these two add together is going to be 0.03. So if this is 0.025, this will be the remainder 0.005. Correct? And therefore, the number of mole of BrOx minus is going to be 0.005. So this is the first thing that we have to sort out. So once we have the number of mole of both products, then we can try to determine the change in oxidation state of bromine in BrOx minus. So we have two half equations involving bromine. The reduction half equation involving bromine will be Br2 plus 2 electron to give me 2 Br minus. This half equation is known because I know the oxidation state involving the reactant and the product. The oxidation half equation is the one that we do not know, but I know that the reactant is Br2 and the product is BrOx minus. I know that it is oxidation, it's going to lose some electron, but I do not know what this value is because I don't know what is the oxidation state involving bromine in the product. So I'll have a known half equation, I'll have an unknown half equation, then this is a classic type of question involving determining the change in oxidation state involving unknown species given experimental data. But for this question, we have to try to do a bit of work to try to figure out what is the number of mole of your BrOx minus that is being formed. Once we have that, then it will fall back into a fairly standard type of question. So what we will do is we will find the number of moles of my product first. In this case, we're going to use the number of moles of my product to compare mole ratio to the number of electrons, because involving the product, for reduction product is Br minus, oxidation product is BrOx minus, and we do not use the number of mole of reactant because both reactants are the same, both reactants are Br2. So we will focus on the number of moles of product instead, which we have already determined. Mole of Br minus is 0.025, mole of BrOx minus is 0.005. These are the number of moles of the products that we have. Next thing is, I try to determine the number of moles of electron transferred in the process using the known half equation. I have the reduction half equation. The number of mole of electron to Br minus is 2:2 or 1:1. So if the mole of electron to Br minus is 1:1, this means that the number of mole of electrons gained in reduction will be the same as the number of mole of Br minus, which is 0.025. And why are we finding this term? Is because the number of moles of electron gained during the reduction process is equal to the number of mole of electron lost in the oxidation process. Remember, redox is a total transfer of electron. When someone is oxidized, I will lose some electrons, and somebody is reduced, they will gain some electrons. And if they're taking part in the same redox reaction, then the number of moles of electrons involved in this redox reaction, in this transfer of electron, is exactly the same. I lose how many electrons if I'm oxidized will be equal to you gain that same amount of electron if you are reduced by me, correct? So the idea is that electron gain in reduction equal to electron loss in oxidation. So now I have the number of moles of electron lost in oxidation, and I will be able to compare mole ratio between the electron to your unknown species, in this case my BrOx minus. Electron to BrOx minus is 0.025 divided by 0.005, which is 5:1. This one has to be an integer value because each species must gain or lose an integer number of electrons. I can only gain or lose 1 electron, 2 electron, 3 electron. I cannot gain or lose half an electron or 1/3 electron and so on. So this has to be an integer value. Then we know that we are on the right track. So mole ratio involving electron to BrOx minus is 5:1. What does it mean? It means that the change in oxidation state is actually +5. So the reactant is bromine in Br2. Oxidation state for bromine in Br2 is 0. It loses 5 electrons to form BrOx minus. So what is the oxidation state involving bromine in the product? Reactant oxidation state 0. Loses 5 electron, oxidation number will increase by 5 units. Oxidation state for bromine in BrOx minus is going to be a +5. And therefore, we can look at the formula involving BrOx minus. What is the value for X? Where oxidation state involving Br is going to be a +5, then X should be equals to 3, correct? Because +5 for bromine, and then 3 times -2 for oxygen, it will give me an overall charge of -1. So finally, we have already solved for the value for X. X is equal to 3. Answer to this question will be C. Next, how about question 15? Two students are given equal volumes of 0.1 mole per dm cube silver nitrate, sodium ethanoate, potassium bromide. First student mixes sodium ethanoate and silver nitrate and obtain a white PPT. Then add potassium bromide to this mixture. The white PPT dissolves and form a cream precipitate instead. Second student adds silver nitrate to potassium bromide, obtains a cream precipitate. When you add sodium ethanoate, nothing happens. So which statement will explain this observation? Statement number 1, silver ethanoate is insoluble. Number 2, silver bromide less soluble than silver ethanoate. Number 3, ethanoate can oxidize bromide. So which of these statements are correct? If you look at the information given, we know that the topic tested in this exercise will be solubility product. So in diagram form, this is what is happening. In scenario 1, based on student 1, add CH3CO minus to Ag plus, I get a white PPT. And then when you add Br minus, the white PPT will dissolve and I form a cream PPT involving AgBr. The white precipitate will be silver ethanoate. The cream PPT will be silver bromide. Now in scenario 2, when you add Ag plus to Br minus, straight away we will get cream PPT for AgBr. When you add ethanoate, nothing happens. Your CH3CO minus is not able to replace the Br minus. I will still get AgBr as the PPT. So which of these statements is correct? Statement number 1, silver ethanoate is insoluble. The statement is true because when you add Ag plus and ethanoate together, we get a PPT. So statement number 1 is valid. I get this white precipitate form. Statement 2, silver bromide less soluble than silver attenuate. Now this is also true because the system actually favors the formation of the cream PPT as compared to the white PPT. So this would suggest that solubility involving silver bromide is lower. So therefore, it is easier for me to form the cream PPT as compared to forming the white precipitate of silver attenuate. Then number 3, attenuate can oxidize bromide. Totally not relevant because this is not a redox reaction. This is just a precipitation process. Maybe just to add on to that, involving statement number 2. So if silver bromide is less soluble than silver attenuate, then why would the PPT dissolve when you form the cream PPT? So why is that the case? Now, if I look at statement number 2, silver bromide is less soluble than silver attenuate. If that statement is true, then it means that I actually need a lower concentration of my Ag+ to precipitate AgBr. Because it is less soluble, so therefore it requires a lower concentration of Ag+ to precipitate the silver bromide that is less soluble. Then when AgBr starts to form, what it is going to do is it will use up Ag+ concentration in the solution. The concentration for Ag+ will decrease. And when there's a decrease in concentration of Ag+, it will shift the position of equilibrium involving this dissociation. Now, in this scenario that we have here, when you have your white PPT silver attenuate, when you add Br- and when you start to form AgBr, what you're doing is you're decreasing the concentration of Ag+, and actually you affect this dissociation involving your silver attenuate, which is here. So when there's a decrease in concentration of Ag+, because of the precipitation with AgBr, then Ag+ concentration decrease, and if the concentration of my product decreases, position of equilibrium will shift towards the right hand side. It will increase the concentration of Ag+ according to Le Chatelet's principle. So if POE shifts towards the right hand side, this means that more of the salt actually will start to dissolve, and eventually when the AgBr continues to be precipitated, you continue to decrease the Ag+ concentration, then the POE will keep on shifting towards the right hand side until all the white precipitate, which is my silver attenuate, will dissolve. So this is the reason why when you have your silver attenuate precipitate, and when you add Br- and when the AgBr starts to get precipitated, then you cause the white PPT of your silver attenuate to dissolve. So the answer to this question will be B. Statement number 1 and 2 are correct. Next, how about question 16? Propane, benzene, and ethine contain carbon atoms with hybrid orbitals. What is the total number of the 2p orbitals hybridized with 2s orbitals in one molecule of propane, benzene, and ethine? So this question at the beginning, we have to interpret it properly because the question is asking for total number of the 2p orbitals hybridized with 2s orbitals. So what we will have to consider is out of the 2p orbitals, which one of them are involved in hybridization. Topic tested in this question is under Intro to Organic Chem, targeting hybridization. Let us look at each of these components. Involving propane, I actually have 3 carbon. Each of these carbon is sp3 hybridized. The hybridization involving carbon will be based on the number of sigma bond the carbon is forming. If carbon is forming 4 sigma bond, it will mix 4 of its valence orbitals to form 4 sp3 hybridized orbitals. And if it is forming 3 sigma bond, it will be sp2 hybridized. If it is forming 2 sigma bond, it will be sp hybridized. So for my carbon in propane, all of them are sp3 hybridized. And involving the sp3 hybridized carbon, it is going to use its 2s orbital and all its 2p orbitals for mixing. Each of these carbon will use 3 of these 2p orbitals for mixing, and I have a total of 3 carbons here. So the total number of 2p orbitals involved in hybridization will be 9. Each one uses 3 2p orbital. I have 3 of them. Total number of 2p orbitals used in hybridization will be 9. Now how about benzene? Benzene carbon is bonded to 2 other carbon and bonded to 1 hydrogen, 3 sigma bond. So state of hybridization involving benzene carbon will be sp2. I have 6 of this carbon. So each of these carbon will use 2 2p orbitals for mixing, and I have 6 of them. So the number of 2p orbitals used in hybridization will be 6 times 2 is 12. Finally, involving ethine. Ethine, I have 2 carbon. Each of these carbon is sp hybridized because it's forming 2 sigma bond. And the number of 2p orbitals that each carbon is using is 1. one 2p orbital involved in hybridization. Since I have 2 of this sp carbon, the total number of 2p orbitals used in hybridization in ethyne will be 2. So basically, we have worked out for each of these molecule how many 2p hybridized orbitals are involved in hybridization. So the total number of 2p orbitals hybridized will be 9 for propane, 12 for benzene, 2 for ethyne, and total number will be 23. Answer to this question will be C. Question 17. Chloroethene is unreactive to nucleophiles where 3-chloropropene is very reactive. So which statement best explains the lack of reactivity of your chloroethene to nucleophiles? So we have 4 statements. Statement number 1, all substituted alkenes will undergo only electrophilic addition reaction. Number 2, the CC double bond and the Cl atom are both electron withdrawing, and that will stabilize the compound. C, the electrons in a p orbital of the chlorine atom will overlap with the pi bond. D, presence of the pi bond prevents free rotation of the C-Cl bond, thus decreasing the reactivity. Now the topic tested in this question is actually based on halogenal alkane, and when you have a chlorine attached to alkene carbon, what is interesting is the lone pair involving my chlorine can actually interact with the pi bond. There's a bit of delocalization involved, and it can interact with this pi bond, and therefore your electrons are actually delocalized, and because of this delocalized pi system, there's this additional stability associated with it, and we can call this stability the resonance stability. Some of us will call this the partial double bond character. We can use either one of them, and the consequence will be the same. This CCl bond will be more stable than expected, and it doesn't undergo substitution reaction with nucleophiles. So this is the basis involving that. Actually, this is very similar to when you have chlorine attached to benzene. For the same reason, when you have chlorine attached to benzene, the lone pair involving your chlorine will be delocalized into benzene and can interact with the delocalized pi system in benzene, and the resonance stability of benzene will be extended to your CCl bond. So chlorobenzene also don't have nucleophilic substitution reaction. Same reason here. And therefore, we can answer this question very simple. A, all substituted alkene will undergo only electrophilic addition. Actually, not only substituted alkenes. In general, all alkenes do undergo electrophilic addition reaction. So A, not likely to be the answer. Involving B, your C double bond C and chlorine, they're both electron withdrawing, so they'll stabilize the species. Now, Cl group is withdrawing, but my alkene function group is not really considered a withdrawing group, so B is not true. C is my answer. As mentioned previously, the electrons in the p orbital for my chlorine atom overlaps with the pi bond, and because of that, the CCl bond will have resonance stability, so C is my best answer here. Now D, presence of the pi bond prevents free rotation of my CCl bond, so decreases the reactivity. Now this statement is also not correct, because preventing the free rotation of the bond or restricting the rotation of the bond, it doesn't affect the reactivity in any way. So answer to this question will be C. Next, how about question 18? How many constitutional isomers are there with the formula C5H10 that do not contain carbon atoms in a ring structure? Topic tested in this question will be Intro to Organic Chem. We try to draw all the possible constitutional isomers based on the molecular formula C5H8. Question also tells me that I don't want to have a ring structure, so therefore we can rule out cycloalkanes, and we only need to focus on my alkene function group because the general formula in this case is CnH2n, consistent with my alkene function group where there's only one C double bond C. Question also tells me that we want to look out for constitutional isomer, so we don't need to consider cis trans. If we need to do that, then there will be more possibilities. So very straightforward, I just consider alkene, and I just consider constitutional isomer or structural isomer. Now we have to do a very systematic permutation. Usually recommendation is we start from the longest possible carbon chain, n equals to 5. Then for n equals to 5, there's only one permutation. How many different alkenes I can draw for n equals to 5? So you notice we have two possibilities. I can draw double bond between carbons number 1 and 2. Double bond between carbons number 2 and 3. I'll have two isomers for n equals to 5 carbon chain. Next one, I will try to draw n equals to 4. Systematic, start from the longest carbon chain, and then we slowly reduce by 1. So the permutation, it is very systematic. You don't random draw the isomers because later we will have difficulty trying to figure out whether we have exhausted all possibilities. So for n equals to 4 carbon chain, there's one permutation where the methyl group is on carbon position 2. So altogether 5 carbon, but longest carbon chain is n equals to 4. So based on this carbon chain, I will have 3 possible alkenes formed. Double bond between these 2 carbon, first and second carbon, double bond between second and third carbon, double bond between third and fourth carbon. So I have 3 isomers, number 3, number 4, number 5. Now how about n equals to 3? Involving n equals to 3, there's only one way for me to draw 5 carbon, but the longest carbon chain is n equals to 3. It will be this configuration 2,2-dimethylpropane. And for this carbon arrangement, it is not possible for me to draw a double bond between any 2 carbons because the carbon at the center already has 4 bonds. I cannot form a double bond. It is going to have 5 bonds, which is not possible. So for n equals to 3, it is not possible for me to form alkene, and therefore we will rule out n equals to 3. So we have already run through all the possible constitutional isomers. Altogether, we have 5 of them. Answer to this question will be C. Next, how about question 19? 2 reaction sequences with benzene as the starting material are shown. So we have benzene at the center, form X, then form this guy, where the nitro group and the chloro group are position 1, 2 with respect to each other. The second pathway, benzene to methyl benzene, form Y. After that, I'll have a methyl group and an acid group, position 1, 3 with respect to each other. So question is asking which could be the intermediates, X and Y. We have a few permutations here. X is either chlorobenzene or nitrobenzene. So Y, there are 2 options, is either benzoic acid or 1,2-dimethylbenzene. So the topic tested in this question will be involving benzene, of course targeting the position of substitution of the functional groups that is attached to benzene, whether they're 2,4 directing or 3 directing, and can it direct the next group to where we want them to go. Involving X, what if X is chlorobenzene, and what is the directing effect involving my chloro group? Now Cl group, it is a 2,4 directing group, and it will direct the incoming group to position 2 and position 4 with respect to itself. So you notice what your chloro group can do is it can direct the nitro group to position 2, which is what we want in the question. So likely your X will be chlorobenzene. How about nitrobenzene? Nitrobenzene, my nitro group is 3 directing. It will direct chlorine to position 3 with respect to itself. So therefore, the positions with respect to your nitro group and your Cl group will be position 1 and 3, and this is not what we want. So therefore, we have already solved for X. X should be chlorobenzene. How about Y? Now Y, what we have is I'll form methyl benzene first. After that, if I do an oxidation to form my acid group, then my acid group, it is a 3 directing group. You'll be able to direct the next group, which is the methyl group, to position 3 with respect to itself, and I can form the product that is mentioned in the question. But if I were to use my methyl group and I try to sub your methyl group, can I substitute the methyl group to position 3 and form 1,3-dimethylbenzene, which is the option given in the question? Then you realize that actually methylbenzene is not able to do that because methyl group is also a 2,4 directing group. It is going to direct the next group to position 2 and position 4 with respect to itself. It cannot even form 1,3-dimethylbenzene. So therefore, your compound Y cannot be 1,3-dimethylbenzene. It has to be your benzoic acid. So Y in this case will be benzoic acid. So if we have solved this question, A will be my answer. X is chlorobenzene, Y is benzoic acid. Question 20. Which statement about benzene and its properties is correct? Statement A, benzene undergoes nucleophilic substitution reaction with bromine in the presence of AlBr3. B, benzene molecule is planar, so hydrogen can easily undergo addition reactions without the use of a catalyst. C, pi electrons in benzene are able to donate an electron pair to attack a carbocation to form a bond. D, sideway overlap of p orbitals in benzene means the carbon-carbon bonds will alternate between long single bonds and short double bonds. So which of the statement is correct? Pretty simple question involving benzene, obviously. A, benzene, does it undergo nucleophilic substitution? Totally not true, correct? Benzene is electron rich. It should be reacting with things that are electron poor. It will take part in electrophilic substitution reaction, not nucleophilic substitution reaction. A is totally wrong. B, Benzene molecule is planar, so hydrogen can easily undergo addition reaction, which is also not true. Benzene doesn't do that. Benzene is stable, stabilized by resonance, so it doesn't take part in addition reactions. So B is also not correct. C, the pi electrons in benzene are able to donate an electron pair to attack a carbocation to form a bond. This is actually describing the second step involving electrophilic substitution mechanism. So usually step number 1, I will be generating the electrophile. Step number 2, what is happening will be benzene will use its ring and then attack your electrophile. So basically one of the carbon is taking 2 electrons in the delocalized pi system to form a bond with the E+. Then I'll form this intermediate where this carbon is saturated, bonded to hydrogen, bonded to the electrophile, and the portion around that saturated carbon, the ring will open and there will be a positive charge in the benzene ring. So this is a very standard second step involving electrophilic substitution mechanism. So we should be able to recognize this, and it is consistent with statement C. The pi electrons in benzene donated to attack a carbocation to form a bond. So C will be my answer here. Now D, the sideway overlap involving the p orbitals in benzene means that I'll have alternate long single bonds and short double bonds is totally not correct. All the carbon-carbon bonds in benzene, they're equal in bond length and bond energy, so D is not correct. So answer to this question will be C.